Hello and welcome all. I am Naren from School of Chemical and Biotechnology Shastra. This is a short video on a fluid mechanics experiment that we have as part of BTech Chemical Engineering and also BTech Biotechnology degree programs. In this video, we are going to see on head meters, which is calibration of head meter. So we have three different head meters as part of the fluid mechanics lab. So this is a Venturi-meter, this is an Orificemeter, and then you have a flow nozzle. Now this is how the setup looks like. So this is a flow nozzle setup. Now I will zoom in and take you through the particulars of the setup. But before doing so, let us see what is the principle, what are we trying to do in a head meter. Now, what is the use of head meter? Head meters are used to measure flow rate. As you know, the word meter is to quantify. The meter by itself means that we are using to quantify something. But quantify what? Quantify in this case, it is the volumetric flow rate. Now, in process pipelines or in be it in production process or in other applications, fluids flow through the pipe systems. And we need to know how much of the fluid is flowing through it, either in terms of mass flow rate or in terms of volumetric flow rate. So the devices that are used to measure the volumetric flow rate when the fluid, I said fluid, so this can be used in terms of liquid or if it is gases flowing, or one of the devices category is a head meter. Now the head as such denotes pressure drop. So what is the principle behind this head meters? Now we know that pressure drop is directly proportional to the mean kinetic energy of the flow. So I write this term as Ke with a bar to denote that it is based on the mean kinetic energy. It is only proportional and it is not equal to. So that means there is a proportionality factor. So there is a proportionality factor times mean kinetic energy of the flow. This proportionality factor, you might have rightly guessed it by now, is also called as friction factor when it comes to flow through pipes systems. You might have heard this as friction factor. In fittings, you might have heard this as loss coefficient. Now, this is the principle that is being harnessed in a head meter. That means if pressure drop is measured, then that means by knowing the pressure drop, one can measure the mean kinetic energy, and then that means one can measure the average velocity, and from average velocity one can measure the flow rate. Because for a homogeneous flow, for a single phase flow, pressure drop and kinetic energy, mean kinetic energy, are uniquely related. But if you need to use this, you need to know this proportionality factor. So you need to know this coefficient for that particular setup. This coefficient in head meters such as Venturi-Orifice flow nozzles are called discharge coefficient. How we define discharge coefficient is the flow rate of an actual system to the flow rate of a fluid without friction. So when we say flow rate of an actual system, this means this is with the frictional loss. Whereas in the denominator, we have the flow rate. What would have been the flow rate if there was no frictional loss? This ratio is called as discharge coefficient. So that means instead of writing delta P as proportional to half rho u square, we have written this in a slightly different form, comparing the one with friction and one without friction, and then saying that the actual flow rate is equal to discharge coefficient times the theoretical flow rate. This theoretical flow rate is computed on the basis that pressure drop is equal to half rho u square. So that means there is no friction accommodated here, whereas this actual flow rate is 1 with the friction. So that means now if you see this relationship of Q actual equal to CD times Q theoretical, there are three variables. One is the actual flow rate, discharge coefficient, and the theoretical flow rate. If any two is known, then that means the third one can be computed. So the degrees of freedom, you need two of these to be specified. Now, this theoretical flow rate, as you know, is only a function of pressure drop because there is no friction in this. So that means if pressure drop is computed, then theoretical flow rate can be computed. CD is something unique to the equipment. So that means this is what a manufacturer is expected to give for that particular setup. Now that means for a given head meter, if the CD is known, and then if you can measure the pressure drop across the head meter, then the actual flow rate is computed. Now why we need head meter? This is all is the physics behind the equations that drive this system. But why, if at all, we need? So when pressure drop is proportional to mean kinetic energy, why not we have, like suppose if say this is a pipe that's flowing, and suppose if the fluid is flowing like this, why can't we measure pressure at any 2 points using a manometer and gauge like this, and use this itself to measure flow rate? This is a question I want you to ponder on, right? It is not, theoretically it is not possible. There is one another reason why this way is not feasible to be implemented. I will leave this question here so that you can look into it. Now let's come to this setup. Let me just explain this setup a little bit before telling you the procedure of doing the experiment. Now this is a single setup that you have in the lab in which both orifice and Venturi-meter is there. Now this is the sump, or we can say the water reservoir. You have here the pump. This is Orificemeter. This is Venturi-meter. This is the water collecting tank. So this is the collecting tank. You have a small glass tube attached to the scale through which you can see the water that is being collected in the tank. Now let's see how the flow happens. The flow happens something like this. From the water reservoir, the pump takes the water, sucks the water from, this is the suction end, and then discharges like here. It goes like this and goes through both these routes. So both these pipes, water flows through. Now it goes through all along the venturi and the orifice. If you can see here, there are two valves here. If both the valves are open, then water flows through it and then comes to this collection tank, and from this again goes back to the reservoir. Now you can see that there were two valves on this line, which is this one and this one. If you are doing experiment with the Venturi-meter, then this valve should be closed, right? So that water does not flows here. It only flows the circuit of Venturi-meter. So if you are doing experiment with the Venturi-meter, the valve in the orifice should be closed. In case if you are doing experiment with the Orificemeter, so you want to do experiment with the Orificemeter, water should flow like this. So that means this valve should be open, whereas this valve should be closed. So close the valve on the Venturi-meter side and open the valve on the orifice side to make sure that this is flowing through the Venturi-meter. And now let us see a close view of how a Venturi-meter first looks like. Now this is what is a Venturi-meter that is there in an FM lab. Now as you might have known, a Venturi-meter has a throat. A Venturi-meter has a convergence section followed by a throat and then a divergent section. This is how a Venturi-meter looks like. Now the flow I have drawn is from left to right, whereas if you have observed how the flow happens in the pictures that I have shown below, it is shown just a little earlier, it happens from the right to left. So that means the Venturi-meter is fixed like this. You have the flow happening from this direction. So this is the pipe cross section, and then you have a convergent section, then you have a throat, and after throat you have a divergent section, and then again it goes back to the pipe. So this is how the flow happens. You can see in this there are two ports. This port is at the throat, which is the area of minimum cross section, and this is at the pipe entrance. So this is the upstream port and this is the downstream port. Why this is called the upstream port? Because water enters at this port first, so this is called the upstream port, and this is the downstream port because this is the port where the water enters next, because first the water goes through this port, which is the upstream port, which is at the entrance of the Venturi-meter. Now how you will have to do the experiment, let me just quickly go through that. Right, in detail it is given in the manual. So in this video I'm just going to give the salient points. You put on the pump, make sure, like suppose if you are doing experiment with Venturi-meter, keep this valve of Orificemeter closed, open this completely, and then put on the pump. Make sure that this valve is also open. So water will flow through this, water will rise here, go through both these pipelines, but because this Orificemeter valve is closed, water will be just stagnant on this line, it will not flow. Whereas water will flow through this Venturi-meter and it will come to this collecting tank, and from this collecting tank water will flow through again to the reservoir. At a given valve position, so that means let's say this is fully open, at this valve position note down the upstream pressure gauge reading and the downstream. Remember, this is the upstream pressure gauge reading and this is the downstream. So you can note down in this dials the unit system of the dial and note down the upstream and the downstream pressure gauge reading. Then you again slightly close this valve. So you close this valve, again note down upstream and downstream pressure gauge reading. Sorry, I just forgot one thing before. You have to note down the upstream and the downstream pressure gauge reading, and along with that you should also note down the volumetric flow rate, which is the time taken for 5 centimeter rise. You have to note down in this tube. From time taken for 5 centimeter rise in this tube, you will back calculate the volumetric flow rate. So for every valve position of the Venturi, you will note down the upstream pressure gauge, the downstream pressure gauge reading, and also the time taken for 5 centimeter rise in this collecting tank. So you will close this valve momentarily, allow the water to rise in this tank, and over a given mark, like say from 10 centimeter to 15 centimeter or from 15 to 20 centimeter in this scale in this tube, you will allow the water to collect, and that time has to be noted. So your observation will be your upstream reading, your downstream reading, and then the time taken for 5 centimeter rise. Based on this, you will do the calculation and find out what is the discharge coefficient of this particular Venturi-meter setup. Now how will you do this? Because this volumetric flow rate, the actual volumetric flow rate is the volume of water collected over time. Time you have already noted. Volume of water collected is the area of cross section of the tank into, let's say if you have collected for 5 centimeter, which is actually H. So this gives the volume. Time you have already noted. So this gives the actual flow rate. Pressure drop is the difference between the upstream scale reading and the downstream scale reading. Now once you know the pressure drop, you can calculate from this pressure drop what is the theoretical flow rate. Once you know the actual and the theoretical flow rate, discharge coefficient is just the ratio of actual and theoretical flow rate. You can also do regression by plotting the actual flow rate or the theoretical flow rate versus the actual flow rate, so that you have the points and make sure that you draw the regression line passing through the origin, and the slope of this actually gives the discharge coefficient. We will also look how the orifice looks. Now, orifice is a single plate here with a hole. This is a single hole orifice. We also have industrially orifice with multiple holes, something like this. So these are, and it need not be always circular. But what we have in the FM lab is a single hole orifice. So the setup is essentially the same, but the only difference is when you are doing experiment with orifice, this valve should be completely closed. So the valve in the Venturi line should be completely closed. This should be open, and the rest of the procedure is same. But however, let us see about one important point on the upstream and the downstream port in orifice. So in the orifice, this is a close view of the orifice. Water flows like this. Now you can see this is the first port. Okay, so this port acts as an upstream pressure port. So you have the orifice plate here between the two flanges. You cannot see it from outside. And this port is the downstream port. So this is the downstream port. So you have to see to the gauge where this upstream port and the downstream port are connected, and accordingly take the reading. Do note down the least count of the gauge in your observation column. I hope this video will give you a fair idea of how to do the experiment. Please read the manual so that you get a complete idea, and also the corresponding theory and the links given here. This video is just a primer for you to do the lab experiments, and it is not going to supplement the theory or the lab manual. Thanks for watching this video.